SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 9. Today we will just be focusing on this failure mode effect analysis technique. Just a quick recap of what we were doing in the last lecture. We were trying to identify on a systemic basis the various factors related to the noise factors, as well as the several external factors, as well as the signal factors which would be there for an engineering system, and again categorization of those factors as controllable and uncontrollable ones, so that finally the response of the system could get generated. In this sense, we also tried to understand on a transistor circuit what would really be the variability factor which is available more towards the designer, and what is also the controllable factors which are mostly related to the operators, etc. Today we are going to investigate this whole technique FMEA, which is a very important technique for quality control and quality implementation, particularly at the process level. So most of the industries, particularly the automobile industries, etc., are very much into doing FMEA analysis at every level of the parts or components, and also the fitment as regards the assembly processes. So what really is this FMEA? So the term FMEA actually means failure mode effect analysis. It's an important technique that is widely used in industry, okay, and as I told you, big auto manufacturers, and also typically the goal is continuous product improvement in terms of its quality to satisfy some needs of the customer, etc., which are very, very important for sustenance in a business. So FMEA has in fact become the bread and butter of several engineers working at the process control level, and it can be described as a systematized group of activities intended to recognize and evaluate the potential failure of a product or a process and its resulting effect. Okay, so you have to list down the cause of the various failures, and then you'll have to again identify the most important cause. That is the whole purpose of the FMEA analysis. And then you identify some actions that could eliminate or reduce the chances of the potential failure occurring. I'm going to give you a detailed process example of a automotive paint shop, that how FMEA can be carried out in a painting process, where you will understand what I am telling more realistically or practically when we recognize and evaluate a problem and identify countermeasures to eliminate possibly the cause of the problem. And then also FMEA needs to document this whole process, and the whole idea is that once a very organized study of the failure modes with its ratings, as well as the potential actions that could eliminate such failure modes, as well as its ratings are documented, the idea is that in future, if such problems get arisen due to a process decontrol or a process going out of the limits or whatever guidelines it has to follow, you should be able to quickly get it back on track using referrals from the previous documentation that has been done by the industry. So that is why documenting the process is very, very important in this particular case. Okay, so it is complementary to the design process of defining positively what is a design process, what a design process must do to satisfy the customer, and it's a generic approach that can be used to identify failure modes and analyze their effects on the system performance with the objective of developing a preventive strategy. Okay, so that's what FMEA or failure mode effect analysis is about. So the methodology that is typically used for the process FMEA is to, again, the philosophy is really the characterization of the various potential failures and its causes of a particular system. Okay, And the failures can further be characterized by three important things. One is the occurrence, that means how often a particular failure mode occurs. If I am talking about a paint peel off, or maybe let us say a dust spot in a painted automotive body, the idea again is that how often this failure happens, and it goes undetected from the paint stage probably to the next stage of an automotive, which is the assembly stage. So there may be a situation where in a shift of, let us say, about 300 vehicles, about 10% of the paint vehicles, are about 30 vehicles are seen with these dust spots on the painted body. So this is a failure, and so the occurrence there is about 10%. So in this same manner, between processes at every level, whether it's a component coming from the vendor's process to your process, or it's a component produced in house which comes to your process at some stage, you have to identify the failure modes which are creating disturbing influences on the overall quality and occurrence. Okay. Then the question is the severity, that how severe or how serious the failure is. For example, if it is a failure related to the life and death of the driver of an automobile, for example, let us say the wheel nut goes cross threaded and finally it breaks, the particular nut which is used for mounting the wheel. This is now a very, very serious problem concerned with the safety of the operator. So obviously the severity aspect of that failure is very important. So first step is the occurrence, the frequency at which the failure has happened. The second step is the severity at which you are rating this failure to be happening, and then finally is the detection. Okay. So if there is a failure mode and it is detectable, then obviously we should be able to recognize that to be relatively not such a serious activity. But then if there is a failure mode where detection becomes a real issue or a real problem, and it can go undetected to all the way to the customer, and that becomes a very, very critical issue. So if I were to develop a mathematical rating system to identify all these different aspects associated with a failure, like let us say the occurrence, the severity and the detection together, and then we analyze how severe, how frequent and how difficult to detect, then those are the kind of failure modes which you really should identify and never let it happen, okay, on the whole process assembly. So that's the whole governing philosophy of the FMEA process, and we like to now evaluate such the failure mode for a particularly a paint shop, as I told you, where we will actually try to rank it in order. So first of all, let us study the methodology, the mathematical methodology of detecting the ranking order, and then identifying the most ranked ones to the least ranked ones, and then tackling those most ranked ones, so that there can be a chance of elimination of all such failure modes which have a high value of occurrence, quite severe, and then very low detection possibilities, okay, or the difficulty level is very high of detection. So we will do that, but prior to that, let us actually study how the ranking is done. So principally, the implementation of the FMEA process necessitates the following steps. Okay. First of all, you are identifying the problems for each operation, and that can be identified mostly at the local level. For example, when we are talking about a automotive shop and we are talking about problems related to, let us say, the paint or the assembly of the particular component into the final vehicle, then the group or the governing members who are associated with the fitment would be the best people, and that is basically also the people who are online and who are doing the fitment, okay, who would take a decision on that particular component or that particular failure mode. Okay. So basically there are many ways of representing that thought process which comes out through a committee discussion or a brainstorming, and one of them can be, for example, cause and effect diagrams, which I will illustrate a little bit later. It's also known as the Ishikawa diagram or the herringbone diagrams. Then for example, the potential causes of the machine failures could involve mechanical or electrical subsystem failures, tools, inspections, equipments, operators and so forth, and this has to be very clearly laid out as the exact problem or exact problems, and what is the responsible reason for the particular problems. And then you can use flow process charts as basis for understanding the problem, which provides a common basis for communication among the committee members. also collect some data from time to time and analyze if necessary if the data is already available, or if it is not available then you collect and analyze whatever be the basis. So all these important things go towards really the identification of all the problems coming in a certain area on a given period of time, okay. And you have to directly relate the concerned local manpower which is assisting in fitment of these parts or components or even a process, okay. So the process level personnel are really involved to do the brainstorming, because they are the best people to actually comment on the quality of the product at that particular level and the potential failure modes which may be able to go out of that particular production level, okay. So now you prioritize the problem. So you have studied all the problems by means of this statistical analysis, and I will actually give you some basis. There are about 7 odd different tools of quality control which is nothing but a process, and then based on these processes you should be able to quickly and organized way collect the data of problems related to a certain process or to a certain component, okay. And so that has to be documented in that particular order. So I will discuss it towards the end of this FMEA activity. First of all, let's focus more on the FMEA as of now, but there are organized methods in which this process data will come out, which will identify these are the problems, these are the potential failure modes associated with the particular stage of the process or the system that we are concerned with, okay. So then you prioritize the problems. Once you have identified the problems, you prioritize the problems, and the priorities are based on rankings, and these rankings are again done by those personnel who are involved in the process level itself, okay. And so the rankings basically would mean that you will have to rank how frequently the problem happens, how severe the problem is, and then how difficult or easy it is to detect the particular problem, and then you basically rank each of these categories and multiply the ranks to each other to formulate something which is now known as the risk priority number, okay. So supposing if the defect is high frequency defect, it occurs more, then obviously the rank should be more. Similarly, if the severity of the problem is very high, the rank should be more, and vice versa. Let's say you have a scale of 0 to 10. So if supposing we are we're just talking about, let's say, the engine mounting nut on the hood area of the particular engine, okay. So here the nut needs to be of high quality. Obviously the nut is going to hold the torque of the bolt. The nut is typically welded in the body, and there is a reinforced bracket which is used to hold it, and obviously there is a engine mounting cross member which comes in the bottom of the engine to support the engine, which actually gets held to those particular nuts in the body. And so the idea is that here we cannot afford to have any cross threading, okay. So because if there is a cross threading, there is a possibility that the bracket of the engine may come out from one of the sides, and it may result in some kind of failures associated with that engine mounting step. So you'll have to study that what is the severity level of this problem. This is probably one of the most severe problems which would come out in comparison to something which is related to aesthetics of the vehicle, for example. Although sometimes the strategy of the management is also involved to make or call on such a decision. Maybe it is very important that these issues related to, let's say, the painting of the body of an automotive is given priority over functional requirements sometimes. So obviously we will have to at least make a system where the painting defects are also equally at some particular level. So the idea is that more on a shop basis you identify your own problems and how you are contributing to the process, and then prioritize based on the ranks or the risk priority number that you are given on that particular shop basis. So for a paint shop, for example, a paint dust may be of that critical importance which is probably the same as the engine mounting members cross threading for the assembly shop, okay. So based on that individual area you can mark the rankings accordingly. Then obviously you have the detectability of the system, how difficult or how easy it is to detect. So if it is a problem which is very hard to detect, then obviously the rank of that particular problem would go up in a 0 to 10 scale, and if it is easy to detect, then the rank would be slightly lower. So this formulates the RPN. or the risk priority numbers, and now you organize on the basis of decreasing order of the RPNs, and obviously the first RPN, which is the highest number, would have a very high occurrence, a very severe problem and very difficult to detect situation, or vice versa. Okay, so you in order of RPN now analyze the problems, and the goal is that you should start eliminating at least the first 3 or 4 problems to a totality, and then study what is the level at which the problem gets resolved or sorted out, and then study the next 3 or next 4. So you should not prioritize yourself towards all of them, but study maybe the first 3 or the 4 RPNs or the potential failures and eliminate them, and then go to the next ones. Okay, and then there may be some where the occurrence may not be that high and the rank may be lower, so obviously those would be in the lower category. So you use appropriate tools to analyze the problems by making use of the data that has been characterized in the various formats to map this RPN or the risk priority number, and then obviously you implement some of the suggestions given by the process engineers to reduce them, and that way you are able to actually see how the RPN is varying after the improvement. Okay, so basically when you have the identified failure modes and an RPN associated with it, you can always do a countermeasure or a counteraction so that those modes get eliminated, and then again rate the RPM after the countermeasures have been implemented on the system and see if the RPM is coming down. Okay, so there is a tracking of how you are eliminating the highest occurring, most severe, difficult to detect defects, okay, on a very organized manner, and the mapping is given by the best person to give this mapping is the person who is associated with the process itself directly. So you are having an RPN number and you are trying to reduce the RPN number by giving the countermeasure or identifying the countermeasure, and then finally the idea is that once all these RPNs are reduced to the next level, you can take the next 3 RPNs and again try to reduce them to the next level, so on and so forth. So that way you can actually do a evaluation of the whole process by doing this whole analysis, and this analysis essentially is known as the failure mode effect analysis. So I think I have made enough theoretical introduction, so we will close this module here in the interest of time. The next module we are actually going to do an FMEA on a paint shop, as I illustrated, for a particular defect which happens, and we will close on here by a take home message that this theoretical introduction what has been happened in the RPN would actually be implemented now, and you will see how the tables are made, or you have to very critically examine what is the format in which this whole FMEA would be made, which you are talking or which you better know as the documentation related to the FMEA. Thank you so much.